Let's talk about inverse functions. So again, remember, chapter 5 we're doing is we're revisiting a lot of the same topics that we've already done so far in calculus, but now what we're doing is trying to look at different types of functions than we did before. So inverse functions is our next one. So some facts that we want to remember about inverse functions. So these are things that you would have seen in high school or pre-calc or college algebra or something. So they only exist for one-to-one functions. So one-to-one functions, remember, so a function passes the vertical line test. A one-to-one function says it passes both the vertical line test because it is a function, and it also passes the horizontal line test. Now, if you remember the next fact about what happens if you compose an inverse with its original function. Both ways, you're going to get x. So you can imagine basically that they cancel each other out. So this was the fact about compositions, and then the domain and the range of a function and its inverse. What happens to those two? Well, if you remember when we algebraically find inverses, we switch the x's and y's at some point. So when we try to find this graphically, we reflect it over the line y equals x. So the x's and y's, they switch, and so the domain and the range, they're also going to switch. So the domain and range of these switch. So what that means is the domain of f becomes the range of f inverse, and the range of f becomes the domain of f inverse. So these two switch with each other. And we saw that a lot when we looked at exponential functions and logarithmic functions. So we saw that with asymptotes and all these things. So now some calculus facts. So these are like pre-calc facts. These are ones that now we can talk about in terms of calculus. So the first is that if f is continuous, then its inverse function is continuous. So if you think about graphically, graphically how if we find an inverse is we're going to reflect this over the line y equals x. So whatever I have drawn here, if I reflect this over the line y equals x, I don't expect to all of a sudden add a new discontinuity somewhere. It seems that wherever this is going to be defined, the inverse is also going to be defined here. So we have a nice continuous functions in both of these. Where f is increasing, the inverse function is also increasing. So basically they just do the same thing, and the same thing with decreasing. If one's decreasing, the other one's also going to be decreasing. And then this last one, though, this is important, that if f is differentiable at c and the derivative at c does not equal 0. So if we don't want there to be some type of horizontal thing, then the inverse function is going to be differentiable at c. So as long as it's differentiable and the derivative does not equal 0. So we're going to try to understand maybe why is that important. So let's take a look now at a little bit of the derivatives. How do we calculate the derivative of an inverse function using some of these facts? So what we have here is we have f of f inverse of x equals x, or f inverse of f of x equals x. I'm going to start with this first one, and we're going to see what happens when I try to take the derivative of it. So if I have f of f inverse of x is equal to x, just like when it comes to implicit differentiation, if I have two things that are equal, if I take the derivative, those two things should also be equal. So I'm allowed to take the derivative of both sides with respect to x. So I'm going to do d dx of f inverse of x is equal to d dx of x. So now I take the derivative of the left-hand side. When you see a composition of functions, the first rule that should come to mind is the chain rule. That's the rule that we had of taking the derivative of a function inside other functions and so on. So the chain rule says that I'm going to take the derivative of the outermost function first. So I'm going to take the derivative of f, I'll call it f prime. Then I replace the inside. Then I multiply this by the derivative of the inside function. So I'll just call this, say, d dx of f inverse of x. Now, because it's a little tricky to do, how do you do prime notation when you already have an inverse notation up there? So I just prefer this notation. Then I take the derivative of the right-hand side. The derivative of x is just 1. But the goal is to try to figure out what is the derivative of the inverse function. So that is exactly this, the derivative of the inverse function. That is this piece here. So to find this, all I have to do is divide over this piece. So I see that the derivative of f inverse of x is simply 1 over f prime of f inverse of x. And that's it. This is how you define the inverse function, is you're going to take the derivative of the function, and then you're going to plug in what the inverse function as a whole is, without having to try to take the derivative of that. So this is nice. Now, this is where this last statement comes into play, which is why we care about this. We said, okay, f is differentiable, that makes sense. I'm taking the derivative. But also, I don't want the derivative to equal 0, because if the derivative is equal to 0, then I'm trying to divide by 0, and that's never a good option. So that's why we need to make sure that we just have a well-defined expression here by making sure the denominator does not equal 0. So there we go, a little bit of inverses. We're going to keep doing this, and this will help motivate some new types of derivatives of inverse functions that we all know and love.